So this is 6.4, part 2, and we're going to talk about Bessel's function today. So Bessel's function actually has a lot of applications. There's applications in acoustics, heat flow, and electromagnetic radiation. Well, let's start off with the definition. So Bessel's equation of order V has a differential equation of the following form. And this is for V is greater than or equal to 0. So the solution to this uses Frobenius from the last section that we did. And pretty much you have to clear your leading coefficient. And so when you clear our leading coefficient, we can pretty much see that x equals 0 is a singular point. And we need it to be regular, so let's just double check that. Our p of x is going to be our x times our big P of x, which in this case is just 1 over x. So P of 0, which will be our center, is going to equal to 1. That's going to equal to P naught, which is equal to 1. And so that clears, so it looks like it's regular. And our Q naught is going to be minus V squared. We're plugging that in, 0 in there, which we'll need for our incidental equation. So our incidental equation, so plugging in P and Q, P naught and Q naught. So we use Frobenius. Remember plugging it into the equation. We have to use R equals the positive V first. And we'll take the first derivative and second derivative and plug it into the equation. And I'll let you do that if you want to do it and check your work. And of course, we'll plug it into this dE so we don't have fractions. And you come down to a to the k equals minus 1 k plus 2v a to the k minus 2. And then you start plugging in to k equals 0, k equals 1. And this is actually a little bit drawn out, so I'm just going to cut to the chase. You plug in k equals, well, not 0. 0 is not going to work. 2, 3, 4, etc. until you can figure out the pattern. And the pattern becomes so to build this further, we're going to just look at an example of this. For V is equal to 3, we get a to the 2n you get 1 plus 3. See, we just plug in here, here, and here. 2 plus 3, n plus 3, a naught, which simplifies 4 times 5 times 6 to n plus 3. And so what I want to point out is a naught is arbitrary. That's our arbitrary constant. You know, like in the last section, we would plug in a naught equals 1, because you could plug in anything you want for it. And then later on, that's just one of your solutions. Call it a different arbitrary constant. So we're going to choose, see what we want to do is fill in the rest of the factorial. So we want to choose a naught equaling to 2 to the third. And the reason for that is because we have 2n here. Remember, v is 3, and we know from the original it's going to be 2n plus 3, and so that's what we need. And then, like I said, then we're going to fill in the rest of the factorial, so that'll complete that and make it a complete factorial. And so we do that, and we plug it in there, and we get a to the 2n. So again, I'm just going to replace this with this. So let's bring these in and multiply. This becomes n plus 3 factorial. And this and this. We get 2 to the 2n plus 3. And the n factorial is still there. And then we have an n plus 3 factorial. Those two. So our solution becomes and we could clean it up a little bit because we do see these are our same power. Whoops, I did forget a 2n plus 3 there. So we see, okay, so we could clean it up. We do see these have the same power. So if we want to do this process, remember we're trying to solve for any v. So that was just an example for v equals 3, okay? So in general, where v is a positive integer, is positive. It's an integer, except it's positive. Counting number. We're going to choose our arbitrary constant to be, so here, remember v was 3. We want it to be v. So it'll be 2 to the v, 3 v factorial. 1 over 2 to the v factorial. And so our a to the 2n, it'll complete it. It'll be 2 to the 2n plus v. Again, that's the, from Frobenius, the plus v was added from the outside of the series. N factorial, and then n plus v factorial. And then our solution is minus 1 to the n. So this is our actual solution. And what if v is not a positive integer? Means we just are going to write out, we're going to just keep out our x to the v. Everything else can be written inside. Like so. So the only thing we do is, instead of 2n plus v and combining these, we keep the x to the v on the outside. So now, if I want to remind you, so we call the gamma function, if you have x plus 1, it's x gamma x, which is x factorial. So we're going to incorporate this into our formula there. So what we want to do is convert to the gamma function. So using this formula right here, if I have, just add a 1 to that, n plus v plus 1, that would be n plus 1 gamma, n plus v, gamma n plus v, which is equal to n plus v factorial. So it looks like I could just replace n plus 1 factorial with this gamma function. So let's do that. So that becomes, y1 becomes, so then we get the following definition. Becomes our first solution. Remember, it was plus or minus v were my r's. So I just replace the v with minus v in this equation, and that becomes our second Bessel function. And it becomes minus there too. Just everywhere you see a v, you replace it with a minus v. And these are called so the first solution to this Bessel equation, it's the positive one, as we mentioned. It's the first solution, gotten from Frobenius. And if you want to recall, v and minus v were the two roots to the initial equation. So we have a couple cases here. They're the same cases of Frobenius. So if v is not an integer, then y2 is equal to, that's a v, sorry, the second one. And basically y is equal to c1 jv of x plus c2 j minus v of x is our general solution. Case 2. If v is equal to an integer, then y2, it's a different function. y1's the same one, it's j of v. Remember that first solution's guaranteed from Frobenius. And here's the formula. And this can be expressed as a limit. And our solution, our general solution, y, is c1 jv of x plus c2 y v of x. So if the denominator for that y function is 0, then we take the limit as t approaches v of y of t of x, which is y v of x. So when we subtract R1 and R2, since they are the same thing, it will be v1 minus a minus v2. Well, v1, because they will be equal. It's always, you get 2v, okay? So the question is, what if v is equal to 1/2? You get double, it becomes 1. The answer is it's okay. Our y2 is j minus v of x is okay. We don't have to use the second y because, again, our criteria, we've kind of lessened our criteria to be, instead of the subtraction, if they're not an integer, you can use it. So this still holds. Half's not an integer, so therefore that formula can be used. A couple examples. So here we can pretty much see v is equal to plus or minus 5. And so since it is an integer, we can just write out our general solution. Let me just write a general solution. So j 5 of x, you plug in 5 for x, plus c2 y of minus 5 of x. That's it. So that's my v squared is 1 over 16. So v equals plus or minus 1/4, which is not an integer. So we just need to write our general solution. Here's y equals c1 j of 1/4 of x plus c2 j of minus 1/4 of x. That's it. You can actually graph these on Wolfram Alpha.